Ladies and gentlemen, as we are about to begin, please be ready. I have a few housekeeping notes before we start today's programs. First, I would like to seek your cooperation in completing this seminar. Kindly switch your mic to silent mode to avoid interruption. Thank you for your kind cooperation and attention. Assalamualaikum and good afternoon, ladies and gentlemen. Hi, my name is Nurzata Yusrina binti Zulkana. It is my pleasure to welcome you, and I also would like to thank you for joining us for this special soil stabilization using mechanically stabilized layer with Geogrid. Before we move on, let us begin with the recitation of dua that will be led by Muhammad Haris Hanafi bin Muhammad Hafiz.
Al-Fatihah. Auzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillah rabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajmain. Sesungguhnya kami berhimpun pada hari ini di dalam majlis ilmu yang bertajuk Soil Stabilization Using Mechanically Stabilized Layer with Geogrid bagi menyatakan kesyukuran di atas kurnia-Mu yang tidak ternilai. Jadikanlah kami hamba-hamba-Mu yang sentiasa bersyukur sama ada nikmat yang sedikit, lebih-lebih lagi nikmat yang melimpah ruah kepada kami. Ya Allah, Ya Rahman, Ya Rahim, sesungguhnya Engkau Maha mengetahui bahawa kami di sini ingin menimba ilmu-Mu yang sangat luas bagi mengembangkan potensi kami sebagai hamba-Mu yang Engkau redai. Justru berkati dan rahmatilah perhimpunan kami ini Kurniakanlah kepada kami ilmu-Mu. Sinarilah hati-hati kami dengan cahaya dan hidayah-Mu. Semoga dengannya kami mudah menerima dan menghayati serta mengamalkannya. Rabbana hablana min azwajina wa zurriyatina qurrata a'yun waj'alna lil muttaqina imama. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Walhamdulillahirabbil alamin.
Amin, amin, ya Rabbal Alamin. Thank you for the recitation of doa just now. At this time, I would like to pass to Dr. Tuan Nur Hasanah as our moderator for today to deliver the opening remarks and begin our session.
Thank you, Ms. Zato, our MC for this evening session. Assalamualaikum and very good evening. First of all, I would like to welcome our guest speaker and all of the participants, and thank you for joining us today. Okay, for your information, today we live at our own place, so maybe we have some technical and internet connection problem. I hope everyone can understand it. Thank you. So before the presentation begins, it is now my pleasure to introduce our guest speaker. I are Dr. Loke Hooi. Okay. Dr. Loke graduate Doctor of Philosophy in Geosynthetic and Geotechnical Engineering from United Kingdom. He awarded Bachelor of Engineering in Civil with first class and graduated Master of Business Administration from the same university. So he has been involved in the research, manufacturing, consulting, design, and teaching of geosynthetic for more than 25 years. He also has a lot of experience with several multinational companies dealing with geosynthetic as a senior manager position. He is also active in the development of Malaysia test standard for geosynthetic, and now he is the business director of Tensar International Limited. Okay, without further ado, I would like to invite our speaker to deliver the presentation. Hi, Dr. Luke. The floor is yours.
Right. Can you hear me all right, everyone?
Yes, clear.
Right. So first of all, I'd like to say a big thank you to Dr. Hasana and also the team from UTHM for inviting me here to deliver this topic. I've spoken about this topic before, some time back, I think several months ago. It's a sad thing that I can't be at the UTHM to be with you guys to have more interactions because of the pandemic. But nevertheless, through technology, I think we can still get together and make this presentation. So can you see my screen now?
Not yet.
Not yet. So let me just, or should I share my screen? Hang on. Okay, I thought I already shared my screen. Okay, one more time. Can you see now?
Yes.
Okay,
Yes.
now you should be able to see. All right, that's good. And I'm just going to do, what do you call that? Display setting, duplicate slides. Right, so you can see the big screen right here. Let me just hide the video panel so that it's very clear. Right, so it is very exciting to see a lot of invited guests in this construction industry week. It's a great organization. Congratulations to the team for putting this few days of organizations into this, and I think this is a great effort, and again my congratulations to all of you who have made this happen. So the topic of the presentation today is regarding about soil stabilization using mechanical stabilized layer with geogrids. Now the topic itself has got several key phrase, for example, soil stabilization. So I like you to remember that word very carefully. I like you to remember the other word is a mechanical stabilized layer. And lastly, the word geogrid. Okay, so I don't don't be discouraged if you don't understand what is Geogrid. I will show you some examples, and in this presentation, I will go very slow. It's a structured presentation, and I'll show you a lot of videos of the application as well. Right, the question here is that why is it so important to have soil stabilization? Why is it so important? We talk about ground improvement, we talk about reinforcement. Those are beautiful terms. You know? Those are terms which is synonymous to ground improvement. But not many people really heard about soil stabilization, or the word stabilization is used wrongly. And this is what we try to correct, or this is what will be the objective of this particular presentation. So why is it important? You may come across words like working platform or applications like working platform. And you can see here that this is, if I can just get my pointer, you can see here, this is the working platform. If you compare the size of this particular truck, just imagine the size of a human being is so small compared to huge machinery like this. And if you do not have a firm foundation or a working platform, then you will not be able to support this particular vehicle, and it will just, in Bahasa Malaysia, we call it tumbang, you know, it will just collapse and it will not work. So, and that is why the stabilization of the ground is very important. In fact, if you may ask, is there a design or a guide for working platform? The answer to that question is yes. There is a design, and I show you one example here. This is the European Federation of Foundations Contractors, which is the EFFC/DFI. DFI simply stands for Deep Foundation Industry. So you have got a document here to teach you how to actually design a working platform. What is interesting here is to see this little picture here. Now, this is a European document. And if you notice this picture, I don't know how many of you would notice this picture. When I checked back the record, it shows that this picture is actually from Malaysia. It is actually a tragedy that's happened back in 2016. And this is quite common, unfortunately, in the construction industries that we are facing in our country, okay? You can also see here in that particular document, if you look at the appendices, you can see there's a ground engineering magazine, which is talking about bearing capacity of a geogrid stabilized granular layer on clay. So there is a design method already in place, and this was published in 2019 by Lee and Matthias. So it is not uncommon to see that we do not know about geogrid stabilization. It's already a published document. So any of you, particularly those students who will be graduating very soon and coming up to the industry, and if we enter into this particular industry, I would strongly advise that you get hold of this document. So that's a working platform that you will need. Just to let you have a look at the video, and this is something which is actually quite common. Where can I play the video now? Oops.
Tell what push. Push.
So you can see a crane is carrying something very heavy. And then you have got a problem if you do not really take care of the foundation or a working platform where the heavy vehicles is going to be supported. All right, so you've got condition like that. If you look at this is really a very heavy equipment. This is a construction in a wind farm. And I'll show it to you why is it so important to have a good working platform, because it's going to save a lot of time as well as money. All right, so for heavy crane transportation, we need to have a stabilized platform, okay? We need to have a stabilized foundation. For railway ballast track, so this is also a very important application. You can see the railway, you can see the track, and you can see the ballast, which is here, and you can see the geogrids, nice geogrids, and you can see the train just passing over the geogrids. So it's for railway balance track. And also for subgrade stabilization, you can see rows of geogrids has already been laid out over very, very soft material. And this is actually a project in Korea, whereby the client is trying to, this is an industrial area development, but getting access to the site is completely impossible. What has been done here is to lay a geogrid. You can see the footprints over here. I think I may have some other photographs to show you that later on. For road constructions, okay, and if you notice, these are all the loading coming from the top. All right, so your geogrid is laid. This is how the geogrid is laid. And then you have got your construction vehicles lying on top, and you use your aggregates or the base cost material, which is a very good material. And there are reasons for why you're using such a good material over the geogrids. Right, so this is what we're going to talk about in our presentation today. We're going to look at the performance review. Okay, it's very important. The word performance here is actually the most important thing. Sometimes if you look at the whole design alone, you can see that there is, in fact, you have to depend on what we call empirical design. Empirical simply means that you run real trials and you look at the results, okay? You can't actually make an equation or have a formulation. It's quite impossible. And through the performance, then you try to make a formulation out of this, all right? And that's why we talk about performance, okay? A lot of projects, or a lot of, for example, the design of road pavement is all purely empirical. And so is design of geogrids for pavements. It's all purely empirical. In other words, we put the road to a test. We run heavy vehicles, different kind of vehicles over it, and we look at the performance. Okay, if there's not much of a rutting, if the road is okay, you don't have a lot of potholes, then we say that the performance is good. So, and this is what we should do. If you want to really test something, you got to look at the performance. It's just the same thing as you buy a TV set. You don't know what brand will be good. So when you buy the TV set and then you try it out and you look at the performance, the color is very clear, it's very sharp, you know, you don't have a lot of problems at all. And you say that, okay, that particular brand is good. Why do you do that? Because you have already seen the performance. So performance is what we need, okay? Next thing we're going to look at is what geosynthetics, all right? So the geosynthetic is basically a generic name. So geogrid is a subset of geosynthetic, all right? And then we're going to look into this function. Is it a reinforcement function or is it a stabilization function? So you can see that reinforcement, another term for that is called tension membrane, and stabilization, we also call it confinement. So we got to identify what function is it. Is this geogrid going to perform, or this geosynthetic is going to perform? Okay, we're going to look into the evidence of the performance. I'm going to show you some tests, real tests. As I said, we got to do trial in order to determine the performance. And then I'm going to explain how this mechanically stabilized layer actually work. What are the parameters that you need in order to make it work? What are the parameters in the geogrids in order to make it work? So having looked at the performance, as I said, then only we look at, is there a way to design stabilization geogrids? And the answer to that question is yes. And last of all, we're going to look into what properties do we have to specify, or what properties are important to ensure that the geogrid actually performs. Okay, so these are all very important questions. And at the end of these presentations, I also formulated 3 questions, which I will ask the audience, and try your best to answer the questions if you can, and we can have some interactions during the session. Right, so the first thing here is to look at the performance. What do we mean by performance? And this is what I talk about performance. As I said, you don't know how a geosynthetic will work, but you put in some stones and then you drive your vehicles over it and you see how it performs. So this is a video just to show you that. And you can see that this is a geogrid. And You also have what we call a load, and you have got a construction vehicles over it. Okay, and you can see that the soil is very, very soft. Here is again another performance. So in this layer, I'll just stop it for a while. Oops, sorry. Just go back. If I can just provide you some background. So here is only about 300 millimeters of fill aggregates, and below is actually a layer of geogrids. Okay, the one that you saw in the train ballast. And further down, if you see this particular dump truck, this is about 55 ton. And further down the road here, you don't have any geogrid anymore, and you can see the difference in the performance. So this is, sorry. So this is what happened. Oops, I think I just missed the cue. So you don't see any movements of the stones at all. Here, it's very stable, and the session without any geogrids, you can see that you have got a lot of rutting, trucks simply wouldn't move at all. Okay, so there's a big difference. Here, the stones are all displaced, but the stones over here, whereby you have got geogrids, the stones are not displaced at all. They are confined, they are interlocked, they are held together, and they don't move. Okay, so if you look at the stones here, they are completely displaced, and when they are displaced, they become thinner, and therefore the aggregates will not be able to support this particular vehicle anymore. This is a closer to home view here. This is CDR of the soil is less than 2, which is very soft. And these particular aggregates, you can see the geogrids, you can see the black one here. There's another layer of geogrids here. So there's 1, 2 layer of geogrids. And you can see that the vehicle is very close to the edge. And even though it's very close to the edge, you can see very little movement from moving away from the roads. So very little movement of the stones moving away from that pile. Okay. So that's what we talk about as performance. Now, this is also a very interesting project. I showed you the big vehicle earlier. Now, for this particular vehicle, to mop and demop, it will take you 14 days. So you got to dismantle this vehicle. You have got these trucks who is transporting all the parts to another project site in a wind farm, and then they have to reassemble it again. So the mop and demop part take about 14 days. Now, with the geogrids that we can actually provide for a good access road, this machine need not demobilize. They can actually move on the road. And you can see this movement. So if you look at the size of a human being, it's very small. Even this truck is very small compared to this giant, which is actually used to carry the wind turbine. All right, so this project is actually in Holland. There are numerous, so many case histories to show the workability of soil stabilization using geogrids. So what geosynthetics are normally used in roads? This is an important question that we normally ask. And I just want to show you some of the geosynthetics. So typical solution is that if you have a soft clay, you step over it, you will sink. And if you know that if you have got a wooden platform, you step over it, it will actually float. And the reason for that is because that this wooden platform is able to spread the load to a wider area and therefore reduce the pressure. So, and then it's allowed to be able to support the load. Now, remember that this wooden platform is one whole homogeneous piece, is intact. But when you talk about a material, which is basically a fabric, a geosynthetic, if you put it close to the soft subgrade, you will still have the similar effect, provided that these geosynthetics will not deform. And in most cases, if you put a layer of geosynthetics here, it will deform in this manner when it is loaded. So when you have got loading, it will not be straight, but it will deform like this. Only when it deforms, then only it will mobilize the tensile strength and then it will be able to support the load. Okay, but a lot of engineering drawing, you will see that it is a straight line. It doesn't work that way. This is the real, exactly what is happening when you put a geosynthetic material in between a soft ground and a sub-base material. You will have to deform. The question here is that, do you want to have this deformation at the top? Can we tolerate that kind of failure? Right, that's the question. And in most cases, if you are looking at the working platform, if you are looking at heavy craned access, or for roads, paved roads, we cannot tolerate that kind of huge deformation. And that is why we must have something which cannot deform so much. Okay, and so it's very important to identify the geogrids or the geosynthetic that will help you to do that. And this is what we don't want. You can see fill material has already been placed over a very soft area, and then we have a truck running over it. You can see that a big rut, and the geosynthetic material just breaks and it's not functional anymore. And this is what we talk about performance. So if I ask you, are you okay with this road? And the answer to that question is very clear. Of course, you will say no, you're not okay with the road. So if you are the owner of the road, and I say that I'm going to help you to design a road that will work, and then you pass a truck and you have got this problem, you as an owner will say, no, this road is not going to work. Okay, because there is a deep rut. And this is what we talk about performance, design by performance. Construct a road and see how it works. If it doesn't work with a big rut like this, then you say that it doesn't work. But if it's smooth, then you say the road perform. Okay, same as geosynthetics. We do not know whether a geosynthetic will work or not. And we can only find out by putting a geosynthetic material inside there and to make sure that it will work. Okay, so you can see here a lot of roads, you can see cracks appearing at the top, and after some time you can see a big rut over here, and surely with this kind of scenario we know that the road is not performing. Okay, so we cannot have this kind of performance, especially for important structure like pavements, heavy duty pavements, cranes, access working platform. We cannot have this kind of deformation. So let's look at the variety of geosynthetic over here. Maybe I just thought that I just share some screen. How do I get back to, more control? I'm going to just do a little bit of adjustment here. A virtual background, I'm going to go to none. And then I'm going to, let me see, where do I go now? Oops. All right. Can you see the geogrids I'm holding in my hand?
Yes.
Oh, okay, you can see because I can't see you guys. All right, okay. So just let me explain a little bit. So the first, and I'm sure that you can also see my screen, all right? Okay, so the first one is called a woven geotextiles. All right, and this is the kind of woven geotextiles we're talking about. Okay, so if you look at that, there's no stiffness. All right, so I just use my hand to support, and then you put a load. Okay, so you put a load. There's no stiffness. Okay, so every time you put a load from top, you can see that it will just deform. Right, so this is a woven geotextiles. The next one, we have the flexible geogrids. So this is a flexible geogrids, and they are joined together here. Okay, we call this a junction. All right, this is a flexible geogrid. So again, if I put a load here, you can see that it will just deform. Yep. All right. If it's not clear, just let me know and I'll demonstrate this again. And then you also have got another geogrid, which is welded. You can see the welding, and you can actually break it off quite easily. This is the welding of the geogrids. So this is the junction. So right here is the junction. All right. And this is also very flexible. Okay, it has some better stiffness, but it's also very flexible. Okay. And then you have got another one, which is we call a punch and drawn geogrid. So why do we call it geogrid? Because this is actually in a grid form. All right, and if you put this one, this is very stiff. It will still bend if you put a lot of pressure on it, but it will still bend, but it's very stiff compared to the rest. Okay. So it's very important to have this distinction. Now remember about the earlier slides I shown it to you, whereby the roads start to rut, and this is what we're trying to do. We don't want the road to rut. Okay, we don't want the road to deform vertically.
Dr. Luke,
Yes.
can you explain to us what is the difference between each of these types?
Sure. Yes. Yeah. So as I say, the difference between each of these is the stiffness of the material. So if you look at the geotextiles, this is a textile form. So it's not in the grid form at all. Okay. So you don't have any holes. That's why we don't call it geogrids. And you can see again, the stiffness is very low. Yeah. And this one, this is made from a polyester geogrids, and it's also very flexible. And the thing here is that it does not have a good junction. Okay, so you can actually break this in terms of installation damage, it is actually quite low. Okay, same thing as this, you can see the stiffness is better, but again, you can see that it's not as high as the other one that I'm showing you. And you can also see that you have got poor junction strength. And then you have got this in the grid form. Originally, in the very early days, it was developed using this. Okay, and because of a lot of research that has been going on, instead of a square type of geogrid, this is also a very stiff geogrid. Okay, so instead of this particular geogrid, these new developments comes in a hexagonal shape. Okay, and there's a reason for that. Okay, why we will have to have a hexagonal shape.
It means all of these types, have a same function?
Yes and no. They are not exactly the same function. Some are good for stabilization, some are not good for stabilization. And I'll explain it as I go along.
Okay. Thank you.
Okay. All right. So the most important thing here is to look at the junction. You can see the junction here is very strong. Same thing as this particular junction. Okay. So if you imagine a road which is carrying vehicle and the vehicle is coming from the top, now you know that when you have got something at the top, it will deform. Okay, so it's very important that we look again at the mechanism of loading. So let's proceed on with the presentation. I'll show it to you. So what are the differences in performance? And that's what we want to find out. What are the differences in the performance? And the next question we want to ask here is that what will be the features of the geogrid that influence the performance? Okay, what properties of the geogrid which is important for the performance? So the first one we want to ask is, what is the difference in performance? Flexible geogrids or flexible geotextile compared to stiff geogrids? And then if the stiff geogrid is better, what are the properties that influence the performance? These are the two questions we try to answer. Okay, so we look at tension membrane, which we call it reinforcement, and the other one we call it stabilization, which is confinement. So to answer Dr. Hassana's questions earlier, which function is better? We will look at it and I will tell you which function is better. And again, it depends on what performance that you want. Okay, so I also note down questions on the slide here. Do all geogrid work the same way? Is stronger better? And this is where, as engineering students, when we come out, every time when you see strength, we say, oh, this material is very good. If we look at concrete or steel, we say, oh, they are very strong. Is strength the criteria or is it not? Okay. So let's look at a retaining wall. If you're a retaining wall, this is a retaining wall. In the design of a reinforced soil retaining wall, we put geogrid or geosynthetic in this way, right? So when you apply the load, this is what will happen. So when you apply a load, let's get the laser pointer again. If I apply a load, the wall will try to move this way. As the wall tries to move, the geogrid or the geosynthetic is holding it back. Now, if you look that the load, direction of load is parallel to the direction of the geosynthetic. If that is the case, then the geosynthetic is functioned as a reinforcement. In other words, it reinforce means it implies adding force to hold this wall back from moving outside. So strength become important. Okay, strength of the geosynthetic become important. All right, because the direction of the loading is the same direction of the geosynthetic. And if you look at the reinforced slope or reinforced wall, this is how we analyze it. So strength, as I said, become important. So you need higher strength to resist any failure. And that's what we found out in our soil mechanics class. But for the road or working platform, it's different. Now the loading, the direction of load is not the same as the direction of the geosynthetic. The direction of the load is down, and the direction of the geosynthetic is this way. So is strength now become important? And I demonstrated to you holding up the various geosynthetic, and you can see that as I press down, you can see that no matter how strong the geosynthetic is, it is not going to hold the load. Okay, so if you can still see my samples, this is my samples. This material is very strong. If I pull it this way, very strong than this material. So the tensile strength of this is more than this. But when you apply the load this way, this performs better than this. Okay, and you see the difference now. All right, so it depends on the direction of the loading. And that's very important. Okay, and this has been well researched. You can see that it is very difficult to explain why reinforcing the road doesn't work. You don't reinforce the road, you stabilize the road. Okay, and this is very important. And when you try to use high strength, I will show it to you in a video. If you try to use high strength material, you will have deformation like this. The whole geosynthetic will deform like that. If it deform like that, then the top of the road will also deform the same magnitude as this. Okay, so it's very important to know the direction of the loading. And this is what happened. So you can see here, if the load is at the top, then your deformation is like this. It doesn't mean that this material doesn't work. This material still work. This material will only work when it deforms. When it deforms, then only it mobilizes the tensile force in the geosynthetic. Then the tensile strength becomes important. By that time, the deformation at the top here is already too much. And this mechanism is what we call tension membrane. So tension membrane works only when you deform a lot, then it starts to mobilize the strength and it starts to hold the loading at the top. But this is what we don't want to have. Okay, you saw the performance before. What we want to have is to make sure very little deformation at the top. And to make sure that very little deformation at the top, it also means very little deformation on the geogrids. How do we do that? By restricting any movement of the soil here. So if the soil here cannot move, so if you look at this, once the soil enter into these holes, it hold together by the geogrid, it cannot move. So the stiffness of this material is strong and it cannot move. So when there is no displacement, then there is no displacement at the top here where the wheel load is. Okay, let's look at some of the videos and it'll help you to understand better. So this is what happened, you see? The big difference between a geotextile, which is soft and flexible, you have a tension membrane effect. If you use a stiff geogrids, even though this strength is lower than this strength, these steels perform better because it has a stiffness and the ability to interlock. And this mechanism is what we call stabilization. So that's a key word here in today's presentation when we talk about stabilization geogrids or mechanical stabilized layer. All right. So a tension membrane works like a hammock. Now, how does a hammock work? The hammock only works when you put a vertical load. Once you put a vertical load, then the hammock started to strain and it started to stretch. When it started to stretch, This is where the reinforcement ability or the tensile strength of the hammock comes into play. But it has already deformed, okay? And that's what we don't want. We don't want deformation, or we try to minimize deformation. So reinforcement of the geogrids will take place when you have got tension membrane effect, when you have got a reinforced soil structures. However, for stabilization of the geogrid will take place, especially for road construction, you need stabilization, or when you have got a change in boundary and embankment, or to limit any slip surface failure. Okay, so let's look at this video. You can see now these people are laying a geotextile, which is something like this. And you will find that it is with difficulty that they lay this material. How do I play these videos? Why can't I play these videos? Yep. Okay.
And to position the fabric.
So
rolling it out straight was almost impossible.
It's difficult.
And in the really soft areas, the crew found themselves in a bit of difficulty. With Geogrid, it was a different story. Only 2 men were needed, and it supported their weight with ease. You can imagine how difficult it would have been to try to sew the fabric under these conditions. On the actual levee construction, 1 man could position the grid, 2 roll it out and overlap it. Unlike a geotextile, no sewing is required.
So you can see the difference. One with the geotextile, which is very high strength, but very poor stiffness, and you can't work at all. The other one is a geogrid, which has got lower strength than the geotextile, and you can see that it works perfect. Why? Because again of stiffness. Okay, so is strength important? And as I said, if the loading is not in the direction of the geosynthetic material, then strength is not the criteria. So if you look at here, we are using geosynthetic of different strength, 40 kilonewton, 25 kilonewtons, 20 kilonewton, 30 kilonewton, and so on and so forth. And we look at the sediment. Okay, after 30,000 Loke cycles, you can see that the lower sediment is around here, which means it is about 20 kilonewton tensile strength of the geosynthetic. Compared to a 40 kilonewton strength geosynthetic, it gives you a huge sediment. So strength is not the criteria, okay? As long as the loading is from the top or is not in the direction or parallel to the geosynthetic, strength is not the design criteria. So do not design on strength. Many people ask me in my whole career or in my career in geosynthetic is, they take a geotextile or geosynthetic material and they show it to me and say that, oh, this geosynthetic material is 80 kilonewton. How does it perform? To be honest to you, I don't know. All I can tell you here is that if I look at the material, if it has got very little rigidity or stiffness, then it will not perform. Okay, but yet still, we have seen engineers designing for road pavements, for platforms, for soil stabilization, everything looking at strength. And strength is never in the equation. If you look at the route design manual by Federal Highway of Administration, FWHA in US, strength is never a criteria in the design. It's all about stiffnesses. It's all about thicknesses of the different base course material. Okay, and that particularly for highway engineering students, you will learn that strength is never the criteria. It's always the CBR, in other words, the stiffness of the material. All right. So you can see here, as I've illustrated very clearly, geogrid with strength which is lower than a higher strength right here perform much better in terms of compared to a higher strength geosynthetic. So there are 2 definition. In fact, it's very clear. This is published in the ISO 10319. So what is reinforcement function? Reinforcement function is the use of stress-strain behavior of a geosynthetic material to improve the mechanical properties of the soil or other construction materials. Remember that. It is the use of the stress strain behavior of the geosynthetic to improve the mechanical properties of the soil. Look at stabilization definition. So the definition of stabilization function is the improvement of the mechanical behavior of unbound granular material. That means the granular materials are loose, they are not bound together, by including one or more geosynthetic layers such that the deformation under applied load is reduced by minimizing movements of the unbound granular material. You see that? There's a big difference between stabilization function and also a definition for reinforcement. Stabilization talk about movements of the aggregates. That means if you can restrict any movements of the aggregate of the granular material, then you have less deformation. And that's how it works in stabilization, by restricting movements of the unbound material. And that is very important. If you can understand that, then you can understand stabilization. And what do you need to do to hold all the aggregates together? By interlocking the aggregates, by using a geogrid which is stiff. That's what it says. Okay. So evidence of performance, let's look at some of the evidence. So we know that all geogrid works. All right. However, it is important to know that they don't work the same. So we have seen this. This does not work the same as this. This works only when it deforms a lot. This doesn't deform a lot and it's already working. So performance test is the indicator. It is completely empirical. You cannot design a geogrid like this and say that, okay, 30 kilonewton strength or 80 kilonewton strength. It does not tell you how it works. How it works, put it in the soil and see how it performs. That's how it works. All right, and from there, we try to have formulations of the designed, design equation. So if you look at the design guide, road note 29 or TRL 1132, even the Ashton method, they are all based on performance. Not even one design method to date are based on strength. They are all based on performance. You test it in the real trial and you see how it performs. Okay, so what do we mean by performance? You can't do a test like this. So if I show you this test, this is an index test. You do it in the lab. So you just hang the samples in the lab and then you pull it. And then you pull it, I'm just going to fasten this video a little bit. You pull it until it fails. And this is what we call a quality control test. It doesn't tell you anything about the performance. So you cannot do this test to say that, oh, this is how a geogrid will perform. It does not tell you that. What you need to do is to have this kind of test. This is a performance test. You put the geogrid into the soil, then you run the test. This is what you have done. So you run it to many passes and then you check the rutting. What is the depth of the rutting? Is it deep? How much it form? And by doing that, you will know the performance. Okay, so if you look at this with the geogrid, you can see the road is very flat. It doesn't deform a lot. And you can say that, you can draw a conclusion to say that, well, this test actually worked. The road is still good. Okay, and this is what we call a performance test. All right, so the key performance indicator is very clear. The answer was given to you already, is deformation. So we look at the deformation. If it's deformed very badly, we say it doesn't work. If it doesn't deform, then we say that the geogrid works. So as I said to you, Ashton guide, you can see tons and tons, different kind of trucks, different kind of tandems, different kind of wheel, different kind of axial loading. And what Ashton has been doing in 1993 is that they run this truck up and down. So there's another circle up here, they run it up and down and they see how it performs. So that's exactly what happened in 1958 to 1960s. They just traffic it up and down along this stretch using different kind of vehicles. And then they formulate what we call the Ashton guide for this design of pavement in 1993. Okay, and that's how, again, purely empirical, based on performance. So what we have done over the years is over 30 years, we have done more than 80,000 and sometimes we're exceeding about 1 million EASL. EASL stands for Equivalent Standard Axial Loading. So we have done so many trials throughout from 1992 all the way to 2014, and you can see that these are all performance tests, all right, in order to determine the performance. So the one performance in 1992, in the very start, what we have done is we have done it with these particular geogrids, okay, which is biaxial geogrids. And you can see the performance right here. So these are the geogrids, the SS2 and the SS1. You can see that if we take a deformation about 25 millimeters deformation, you can see, so you read the graph across here. Now, if you are using, so just to give you a little bit of context, if you are using a geogrid like this is the PET1 and PET2. Control has got no geogrids at all. A PP geogrid will be something like that. And then you have got the SS geogrid, which is something like this. Okay. So, and this is the performance. You can see that at a very small passes, you have already a very deep rutting. But whereas with a stiff geogrid like this, you can see the rutting is at the same rutting, you can see the number of passes is much, much higher. In other words, you need to have more passes to give you the same rutting of 25 millimeters. All right, so you can see here, the performance of a stiff geogrid is much more better compared to a flexible geosynthetic material. And then we go into a full trial, which we call the TRL, which is in the UK. You can see a lot of sections that we have done, stiff geogrids and different kind of geogrids. I've shown these particular facilities for you, and there are a lot of literature and publications of these tests. Okay, and these are done generally at 2% CBR, which is about 50 kPa in terms of undrained shear strength, and the thickness of the fill material above the geogrid is about 300 millimeters. So you can see here, without any geogrid, you can see huge deformation right here. If you are using a welded geogrid like this, the white one that I've shown it to you, you can see also huge deformation, and you can see at the subgrade layer, you can also see this particular deformation. Now, if the deformation is at the top, it's still okay. The reason being, you can top it up. But if the deformation is at the bottom, then it will cause more failure to the structure because you cannot top it up. You got to dig it down and then repair this section. And this is what we try to avoid. But if you're using a stiff geogrid, you can see that very little deformation at the subgrade. So as you know, this is 300 millimeters, and you can see very small deformations at the top at the surface of the road. Okay, so you can see here, this is what we call a tension membrane. It settles a lot, and this is what we call a stabilization or a confinement function. You can see here, as you read across the graph, it can tolerate about 6 times or 8 times better than a flexible geogrid. All right. So from this technology, science has developed and moved into this particular technology. So why do we have a hexagonal shape? The reason we have a hexagonal shape is because the wheel load, as a wheel load is exerted upon the geogrids, the wheel load is actually generating a radial stress. And hexagonal is very close to a radial stress, round. Okay, and that is why the geogrid is formed in a hexagonal shape. Okay, and there are merits on this, and I'll show you the test results. So by using a hexagonal shape, you can see that we can reduce the settlement even further compared to a control. So a control just failed at about 2,000 passes. You have developed about 80 millimeters of sediment, whereby at 2,000 passes, the geogrid section only developed 20 millimeter of sediment. And it continues, it's never reached until more than 40 millimeters of sediment, whereby the control section is already failed and it can't perform the road function anymore. Okay, so you can see that this is very clear. So this chart is plotted against Oss Road, whereby you have got the number of easels. So when we talk about a permanent road, we are talking about in this region. Okay, so 10,000 passes is still quite low. You can see if you don't have any stabilization of geogrid, you can see the road already failed. All right. So there's a difference now. Control, you can see that it failed very fast. Then you have got a square type of geogrids, which I show it to you, which is not performing so well. And then you have got a triangular or a hexagonal shape of a geogrid, and it perform much better. You can see that if you take a 25 millimeter settlement deformation, you can see that it performs about 6 to 8 times far better than the square geogrids. Okay, and this is where the technology is what we want to share with you in this presentation. So we moved on now to a more critical or more higher loading. And this is where we use the US Corps of Engineers trial. And in this trial, you can see that this big trucks is moving along the road. And inside here, you can see this mechanism moving. So this wheel is moving inside this big truck. It is a very expensive test, but it's a very important test. We call it the APT test, Accelerated Pavement Test. The reason this is a very important test is you can perform this test in a controlled environment. In other words, you can control the moisture, you can control the temperature, and you can also allow the wheel to run, not channelized. You can run here and then you move to the other side and you run again. And you can construct a road, and after that, you can drive this vehicle over the road and perform the test anywhere you want. Okay, so for this test, we have carried out way above 100,000 easel. All right, so an easel is about 80 kilonewton of loading. So you can imagine how huge amount of a performance test that has been carried out. And you can see that even with 100,000 easel and with geogrids, the deformation is less than 12 millimeter, which is very small. So in the test, we perform a 50 millimeter of asphalt concrete, which is basically asphalt. And then you have got 200 millimeter of base course. The CBR of the soil is about 3%, which is about 75 kPa under shear strength. And this is the big truck. So you see this section just now. So this is the section inside, whereby you have got a wheel. You can see that you have got the window, you can see through. And the whole thing here is temperature control and also moisture control. So it's a control condition. You can monitor it and compare the test results from one section to another section. So inside this particular truck, this is where the wheel is. It's a very heavy wheel and it's not channelized. In other words, the wheel can run in this track or it can run in the track later on, so it can vary the tracking. Okay, so you can, as I said, the wheel can run along here or run along here or run along here. Right, so this is the test and this is very interesting results. So what you can see here is a control section with 50 millimeters of asphalt. You can see that the deformation, the rut depth is 50 millimeters, only about 20,000 passes. And then you increase the thickness of the asphalt to 75 millimeter, doesn't help at all. At the 20,000 passes, is already developed about 20 millimeters of rutting. Okay, and you remember you increase it by about 50% in terms of the asphalt, and asphalt is very expensive. And what you can do is actually, if you add with a layer of geogrid by using a 50 millimeters of asphalt, you can see that it can go on until 100,000 passes with a rutting of less than 12 millimeters. And that is a very interesting and well-performed trafficking results. Okay. So you can replot these in the Ostrod chart. I'm going to skip this so you can see the deformation without any geogrids. This is what is happening. All right, you can see the deformation right here. Huge deformations. If you have a geogrids, you don't see a lot of deformation. That's the layer of the geogrid here. And you can reach up to about 100,000 passes. Okay. We carry out another test, and this is with the Louisiana Transport Research Center. And this is now going way beyond what is 100,000 passes, which is right here. So what we have done here is we do a plate load testing, and this is up to 4 million passes, and this is the real McCoy, if you like. This is where the real things are happening. The actual roads happens around here, not here. Okay, you don't have a road whereby the number of passes of traffic vehicles is less than 1,000. All right, and this is where you can see again, we have somewhere about less than 15 millimeters of rutting. So I mentioned to you what I mean by when somebody comes to me and say that, oh, I've got an 80 kilonewton tensile strength geosynthetic material. How does it perform? And my answer to that question is, I don't know. And I tell you that it won't perform. It will rut. But if somebody comes and tell me that I've got a geogrid which can interlocks, okay, and has got a very good stiffness, radial stiffness, how does it perform? And I can tell you, most likely you will have a rutting not more than 20 millimeters after about maybe 100,000 passes. And this is what we experience, and this is are the results. And I can tell, when you look at this graph, this is the only graph that I've seen in so many literatures that we are able to make comparison. You can find this, you can't find this anywhere in the literature, whereby you have got real performance of up to 4 million passes. Okay. And I also did a comparison here. You can see this line. This line is very interesting. So this is a TRRL results, which I've already shown you until 10,000 passes. We have about 30 millimeters of sediment or rutting. This is the US Corps of Engineers result, 100,000 passes, whereby you have less than 12 millimeters of rutting. And this is the Louisiana Transport Research Center's test, which is up to 4 million passes. And again, you have less than 12 millimeter of rutting. This is also a very interesting result. This is actually done in a state in Montana, in the US, and this is by using a geotextile like this. Okay. Now you look at the results. It started to rut already about 20 millimeters, about 100 passes. And when it comes to less than 1,000 passes, you can see the rutting is almost hitting 55. And this material has got higher tensile strength than this material. So what is the magic? Okay, and that's what we try to explain to you. So let's look at mechanical stabilized layer explained. All right, so this is the real show. Why is a geogrid, which is stiff and which has got holes and we can interlock, perform better than the geogrid, which does not have hole and which is flexible? Why? Look at this. So this is a very interesting demonstration. This is actually, if you look at these two, I think the first thought that you would think about is this looks like a stone. Indeed, it is a stone. All right. So this is actually made from plastic and is shaped like a stone. And inside this plastic, we have got translational sensors and rotational sensors. And this is what we try to simulate rock ballast for railway. Okay, so when we have got these stones, we can track movements. And this research was done actually at Penn State University. And I just want to show you this video. So look at it very carefully. So let me stop this first so that your eyes won't get distracted. So you can see that as I turn the rock, you can see I can look at it at the screen. All right, so if I do a rotation of the rock, which has got sensors in it, you can see the rotation of the rock. Now, if I do a translation of the rock, I jump it here and there, you can see again the movement of the rock on the screen. When you look at this, you will say, wow, this is fantastic. Why is it so fantastic? Because now you can actually see what actually happened in the road. If I take these rocks and I put it together with the real rocks in the road or in a railway track ballast, I can actually track the movements of the rock. And this is exactly what we have done. All right. So if you look at here, this is a piston, an actuator, and you can see that let me stop the video for a while. So you can see that we applied on the railway track, and these rocks is placed directly, slightly above, about 10 millimeters, about 10 centimeter above the geogrids. So one layer, the rock is placed here, whereby there's no geogrids, and one section, we place the rocks directly above the geogrid, about only 10 centimeters above the geogrids. Okay, now look at the performance of 2. So we apply the load. This is a cyclic load, so it's got a lot of vibration. And you can see as you have vibrate, just like a train passing by, the rock will start to move. So remember, one side is stabilized, the other one is non-stabilized. So I'm going to move a little bit. Okay. Look at the rock. So the original position is actually within the red circle. And you can see that the rock is starting to move from the non-stabilized section. And about 50 seconds later, the rock moved from the red circle to the black broken line. And that's exactly what happened. So the non-stabilized section shows that the rock has moved from its original position, whereby the stabilized section with geogrids shows that the rock doesn't move so much from its original position. Now remember, the loading, cyclic loading, is only applied for 50 seconds. Imagine if the loading is applied for 5 years. I don't know where the stones will be. And if you remember the definition of stabilization function, it mentioned very clearly, stabilization is what we try to reduce the movements of the unbound granular material. That's what stabilization is all about. Okay. So what are the features then for geogrid performance to influence the performance? So we also run tests at the University of Nottingham. And for those of you who are interested to read up a lot of literature, there are tons of literature to read. Okay. So why is a square geogrid not performing as well as a hexagonal geogrid? So here's the test. So we run the test at wheel loading in this direction over the geogrids. Okay. So you can see that the 160 means the number of passes. 25 millimeters is the rut depth. You can see the rut depth here. All right, so it means that, let's look at this line. It means that if I need to run 24 passes to give me a rut depth of 15 millimeters. So if you run the vehicles in this way, it's going to be the same. All right, so if I run 82 passes, it's going to give me a rut depth of 20 millimeters. If I run 160 passes, it's going to give me 25 millimeters of rut depth. Now, I run it in a diagonal direction in this way. Okay, so now if I run it at if I run it at 6 passes, it gives me 15 millimeters rut depth. If I run at 17 passes compared to 82 passes in this direction, it has already given me 20 millimeters of rut depth. If I run it 37 passes compared to 160 passes, it has already given me 25 millimeters of rut depth. So it means that if I run the vehicle or the wheel load in this direction, I can achieve lower number of passes. Why? Because there is no rips in this direction. There's no rip of the geogrid in this direction. Let's try it with a multi-direction geogrid or hexagonal geogrid. I do the same test. If I run it at 28 number of passes, I get 15 millimeters. I run it at 75 number of passes, I get 20 millimeters. 132, I get 25 millimeters if I run in this direction. What happens if I run it at diagonal direction? You can see that I still achieve a very high number of passes in order to achieve the same number of rut depth. Why is that so now? Because you have got rib running in that direction. And that explains why a triax or a hexagonal geogrids perform better than a biaxial geogrid or a square geogrid, because the wheel loading excrete out radial stress. And radial stress has to be taken by radial form of geogrids. Okay, so if I take this quadrant and I make it into 4 quadrants, I will get this shape. You see this? Which is the same as this. And if you look at this, this is 1 quadrant for square geogrids, and I put it in 4 quadrants, I get this. Right? Remember, there are 2 questions you want to try to answer. First question is, what is the performance of the geogrid? What differences of the performance? Second question is, what are the properties that give you a better performance? So we already know the answer for the first question. Which one perform better? We know that a multi-axial or a radial geogrid performs better. That answer we already know. So second question we ask here is that what properties for the performance? So the properties that we need is, number 1, you must have stiffness, radial stiffness. Number 2, you must take the ratio between the higher stiffness and the lower stiffness. So we take the ratio of the higher stiffness with the lower stiffness. That ratio must be more than about 0.75. And maybe I can explain this better by looking at a wheel, a bicycle wheel. Now, a bicycle wheel has got a tire wheel. It's very thin. If you look at the racer bike, it's very thin. And somebody at a weight of 200 pounds or maybe 250 pounds can ride on the bicycle, and the wheel doesn't collapse. Why is that so? Very simple. Because the bicycle wheel, even though it's very thin, is held together by what we call the hub. And you can see all these wires. This is called what we call the spoke. The spoke are very thin, and they are connected to the hub, very strong. Okay? And the spoke, each of every one of these spoke has got equal stiffness. Now imagine if one of the spoke has got low stiffness, or imagine if this junction or this connection is poor, the whole wheel will collapse. And that's the reason why the wheel, being so thin, is able to support a load of 200 pounds. And this is exactly the same as how a geogrid is constructed. The junction here is the hub. The rib here is the spoke of the wheel. Every stiffness of the rib is the same. And the junction connection of the rib to the hub is 100% efficiency. And this is where, again, the junction strength becomes so important. So what are the properties to ensure the performance of the geogrid? Radial stiffness ratio, and junction efficiency. Let me repeat again. Radial stiffness ratio. In other words, the stiffness ratio must be close to 1. What happens if the radial stiffness ratio is 1? Some of you may already answer it correctly. It means that it's a perfect circle. All right? If you have a radial stiffness ratio of 1, it means that the circle is perfect. But because it's hexagonal, therefore you don't get a radial stiffness ratio of 1. You get something close to 1. All right? And the third component of properties, which is very important for the geogrid to function as a stabilization geogrid, is junction efficiency. So a wheel load excreting radial stress, and that radial stress must be taken by a radial geogrid, or close to a radial geogrid, or close to a circular geogrid. And that's exactly why it performs over and over again better than high-strength geotextile or a square geogrid. Okay, so again, many tests of the test verification, and this is one done by Steve Weber way back in 1991 and 1992, and it says here, I think 80% of the geogrid performance was due to geometry and stiffness properties required to interlock the granular particles, and only 20% due to strength. Look at this statement, a very important statement. It says that 80% of the geogrid performance is actually due to the geometry and stiffness that requires interlocking of the granular particles. And only 20% is due to strength. See that? Okay. So the rib is important. The opening, or we call it the aperture, is very important. Square is better than round. So you can see that the opening or the apertures, these are all square. You can feel the edge here. All right. And then you have a very high junction efficiency. Okay. And obviously you must have some kind of stability. All right. So some kind of strength. Only about 20% of the strength is enough. All right. Right. So that's how it looks. And it comes in different sizes as well, so that you can use it to be compatible with different aggregate size. So here is the smallest opening size, which is about 33 millimeters from here to here. And then this is about 40 millimeters. And the largest one, which is 60 millimeters, we use these for ballast railway track. Okay. And is recommended for different sizes of aggregates that you put on top of it. What about the zone of influence? So if you put a layer of geogrids here, a stiff geogrids or a triaxial geogrids, you can see the zone of influence. So near the geogrid, you can see a lot of interlocking, a lot of confinement. But as it goes away from the geogrid, as you go higher up in the field material, the influence of interlocking becomes less and less. So what do? Perhaps you may need to have another layer here. Okay. So I've spoken about the performance. I've run through the test, showing you the test. Now I'm going to talk very quickly about the design part. So how can we design it? Is there any way that we can design it? How do we get help? Yes, it's already been established. So you can see that now we know. If I take a granular material unbound, if I add in together with a geogrid of this configuration, I get a composite layer. And this is what we call, and that's what the topic is very important, mechanically stabilized, MSL. Okay. So this becomes a composite. So we call this a mechanically stabilized. What do we stabilize with? We stabilize with geogrids. This is synonymous, we call this mechanical, this is synonymous with when we add cement or lime. Okay, you may have heard about chemical stabilization, we add cement. Okay, so the difference between the two here is that this does not add cement or any lime or any chemical. It just adds a layer of geogrid. This is why it's called mechanically stabilized. Okay, so by putting a layer of geogrids, you can see that the layer at the bottom here will be interlocked. It can't move. Stiffness is there. Stiffness is as good as original. When there's no movement, so again, back to the definition of stabilization, when you have got limited movements, no deformation of the stones at all, you can see the movements in the Penn State University's video. When there's no movement at all, this whole material is very rigid. And therefore, you have got minimum deformation. All right. So when we use this, we can actually save a lot in terms of construction time and also material cost. Instead of using a layer which is 1.5 or 2 times thicker without any geogrids, we can use a layer which is thinner, half the thickness, and it performs much better by giving you better, number of traffic passes. All right. So we can design it. And what we do here is that we have got a factor for structural number in the design. I'm not going to go through the detail of it, but just to let you know that design been established already. So you can see here, so this is your soft subgrade. And then this is your base course material. And normally you put an asphalt pavement over it. And this will be the normal construction. So the new technology is that we put a layer of geogrids directly underneath the base course. Okay, so this is only one layer for subgrade stabilization. If you want to do a pavement design, we call it a pavement optimization, then you will put 2 layers. In other words, one layer directly above the soft subgrade, and then with the sub-base material, and then you put another layer of geogrids in between the base course and the sub-base material. Okay, so let's look at these two design mechanism and how do we do it. So that's how you put the geogrid: subgrade, sub-base, base course, and layer of geogrids here and layer of geogrids here, and then you have got your binder course or your AWC, which is the asphalt wearing course. Now, by putting a layer of geogrid, as we know already, it helps us to increase the bearing capacity. So you can see that you can put more loading here compared with the section without geogrids. We can mitigate differential sediment. You can see the layer of geogrid, the sediment is even, and here you have the highly differential sediment. We can reduce the pavement thickness. You can see the layer of geogrid, the pavement thickness is much lower, save cost, save construction time, and also save carbon footprint or reduce carbon footprint. We can increase the pavement life. With geogrid, you can see more trucks can run over it at a longer period of time. Without geogrids, you can see that reduced number of trucks running over it, and also at a lower or at a shorter number of time. So these are the benefits of incorporating geogrid or stabilizing soft ground by using geogrids. So if we look at the first method, which is called a ground stabilization method or subgrade stabilization method, we use the method what we call the TRL LR1132. So you can see this is your vehicle loading. This is the equation. You have the H, and we are using easel, equivalent standard axial loading, which is 80 kilonewton. And without geogrid, you can see the thickness. By having a layer of geogrid, you can see the thickness is significantly reduced. Okay, so what we do is we add in this structural number, the factor for structural number, modification of the structural number. Now, how do we do this? You can do this manually, or we incorporate into a computer software to help us to do it faster. So you can see that without geogrids, you can have a 482 millimeter thickness. Look at the easel number of easel again. Okay, so you can see that the achieved easel is much more better, and you can see that this is at 222 millimeters of thickness. So you are reducing the thickness more than half. Okay, in terms of using a geogrid. Now, if you talk about pavement optimization, so this is the AASHTO method. So there is AASHTO guidelines. You have seen the AASHTO guidelines already in 1993. And what we have done here is we incorporate the geogrids by using the FSN value as well. So here you can reduce the thickness of the base course, or you can reduce the thickness of the sub-base course. Okay, so in this section, this is without geogrid, and in this section, this is with geogrid. The formulation all there. If you want to go into details of what is all these notations, you can actually refer to the design guide. And here, if you put a geogrid, you can reduce the thickness of the sub-base material. And if you put a geogrid right here, you can also reduce the thickness of the base course material. Now, these are actually good materials, high quality fill, and they are expensive. Okay, so by reducing thickness, you save on material, and also you also reduce carbon footprint. And again, it shows it to you. You can see the number of easel is the same performance, but the thickness are different. All right, you are reducing it more than half, almost half. So 150 against 284, 310 against, so 310 and 310 is the same, but you can also reduce this further and yet still maintaining the same kind of number of passes. Or you can put these to be the same and yet still using the geogrid, then you can increase the number of performance. Okay, so I repeat again, if I maintain the same thickness as a control section, I can still incorporate geogrid, and by doing that, I will increase these number of passes to maybe about 6 times more. Instead of 5 million passes, it can be about 30 million passes. All right, and that's the benefit of adding the geogrids. For working platform, as I explained it to you, there's already a design guide, and this is right here in the Ground Engineering magazine. And I take the abstract of some of the publication. You can see this in the Ground Geotechnical Engineering IC publication. There's already publication of how to design for working platform. This is also incorporated in the designed software as what I've shown it to you here. Okay, and the method that we use here is what we call a t-value method. Right, I quickly like to show you the installation part, and then I'll wrap up with a summary, and I'll open the rest of the time for some thoughts and some reflection of what we have discussed today, and also try to simulate you to think by giving you these 3 questions. So let's look at the installation. Installation is very simple. The geogrid comes in huge row size, 75 meters to about 3.8 meters wide. And you can see how the installation is actually been taking place. So you prepare the ground, and you can see the black stuff are all the geogrids. So this is about 3.8 meters. You unroll it and you just kick the geogrids. One person is good enough to do the job. And you can see that it's very easy to unroll. And once you have done that, then you put your sub-base material over the geogrids, compact it properly. If it is for pavement, then you put another layer over the sub-base and then top it up with a base course material. So this is a paved roads. And at the end of the day, you finish out with the asphalt concrete. So it's very straightforward. It can be designed. Right. So let's talk about the summary in terms of looking at performance properties, okay, and how to specify those performance. So let's look at these 2 mechanisms again. As I said in the beginning, you have got a reinforcement mechanism whereby the geosynthetic material is required to deform, then only it produces reinforcement. But this is not good, because if it deforms too much, then the top will deform also. And this is not a good performance. This is not what we want. This kind of mechanism depends on tensile strength of the geogrid or the geotextiles. Okay, so if you want to design with high strength geotextile, this is probably the effect you will get. And it requires friction and anchorage. All right, and you've seen the picture whereby they try to lay the geotextile in the mud and they sink inside the mud because there's no anchorage. Okay, so you need to have something to hold it outside here. You need anchorage. And this mechanism is what we call tension membrane. All right, it will require a very high strength material, and therefore you increase the cost. What we are saying here is that look at stabilization. Stabilization does not depend on strength. None of the properties here is talking about strength. It's talking about stiffness. It's talking about interlock. It's talking about confinement. It's talking about lateral restriction or restraint. In other words, it's talking about holding the aggregates together from moving to the side or moving to the bottom. You can see that in this case, the deformation of the geogrid is very minimum. And the deformation on the top at the surface of the road is also minimum. That's what we want to achieve. We have seen test over test, performance test over performance test of only less than 12 millimeters of deformation or rut depth. That's what we are talking about. We are not talking about 60 millimeter rut depth. We are not talking about 80 millimeter rut depth. Those are too excessive. Those only happen if it is a reinforcement function or a tension membrane function. So do not be fooled when you see a high strength geotextile or a geogrid. It does not work that way. Okay. So let's look at reinforcement. So in reinforcement, you need strength, you need elongation. Okay, but when it's stabilization, so strength and elongation, these are product performance, is not functional performance. It doesn't tell you how we perform to the side. And that is why I keep on telling you that if somebody comes to me with an 80 kilonewton tensile strength geotextile or geosynthetic material and asks me how it performed, I will most probably say that it will perform badly. But stabilization is what we look at. We look at radial stiffness. We look at radial stiffness ratio. In other words, the stiffness in different direction is more or less the same. And the radial stiffness ratio, which is the ratio between the lowest stiffness and the highest stiffness, is close to 1. So in stabilization, these are the two parameters that we are looking at. Okay, you cannot separate both of them. These come together. These are performance linked to establish the geogrid performance. All right, radial stiffness at very low strain. This is 0.5% strain, and this is very important because road pavement will start to crack if you have more than 3% strain, and therefore we want to restrict the strain as small as possible to down to 0.5%. And we need to relate those stiffness by the radial stiffness ratio. So why is this so important? Let's go back to this graph again. If you look at the square geogrids, the stiffness ratio is very low because in a diagonal direction, the stiffness is very low. Therefore, you produce a low stiffness. But with the multi-direction geogrid, this is where you produce a very high stiffness in different direction, and therefore the stiffness ratio continue to maintain at very high level. Okay, so these two are synonymous together, they are tied together, you can't separate them. And the same thing here, you need to have high junction efficiency. Okay, and the other one is the hexagonal pitch, which is basically the hole, the size of the hole or the aperture of the geogrids. And there are documents already established by the European Organization of Technical Approval, which spells out the description and definition of stabilization. Very clearly, you can see that it's non-reinforcing hexagonal geogrid for the stabilization on bound granular layers by way of interlock of the aggregates. Okay, and there are test procedures already given in this document. And there are also certification. This is a Kiva certifications, which defines the intended use, which is to stabilize granular layers, and the method of testing, and also what are the characteristics and the properties that give you that performance. So coming back to probably my last slide, this is what I have here. You can see these are the properties, performance properties. Remember that, performance properties. That means properties required to perform. So 2 questions answered. What kind of geogrid that give you the performance? Rigid stabilization geogrid. What kind of properties that give you the performance? The properties required are radial stiffness ratio, and junction efficiency. It has been proven to you throughout this particular presentation that these are the properties that are required for it to perform. So as a last slide here, I do a comparison again between mechanical stabilization and tension membrane. All right. So fundamental behavior improves the properties by geosynthetic soil composite. Tension membrane, you're talking about individual structural element. In other words, the geosynthetic material is a structural element. Here we don't. We talk about these two material acting together, the soil and the geosynthetic acting together as a composite material. Now, the geosynthetic strain level normally is very low, so that you give very low small deformation. Now, the strain level for tension membrane is very high, therefore you can see that it strains a lot and high deformation at the top. Okay, the load-induced stress direction is in the plane, and this is out of the plane. Geosynthetic strain requirement, it does not require high strain geosynthetic. This requires a very high strain geosynthetic. Anchorage length requirement, it does not require anchorage length at all. You don't need to anchorage. You don't need to anchor it. Here you need to. If you don't anchor it, then the whole thing will zoom inside the soft ground. Pavement performance rutting, normally very low. And you can see test and test over and over again, even with asphalt is less than 20 millimeters or less than 50 millimeters. Mostly the rut depth will be very high, more than 50 millimeters. The whole thing will just crack. Okay. Pavement performance fatigue cracking normally is very low. It provides stiff support to the asphalt. So the base course material is very strong. That's why it's required to provide stiff support to the asphalt. For tension membrane, asphalt performance supported by deformed layers. So the fatigue level is very high asphalt cannot be supported by a deformed layer because the asphalt will already crack. Effectiveness, more effective, geogrid in same direction as horizontal shear stress, or geogrid with higher strength, less effective, and the geogrid in different direction as vertical stress. So you can see that the geogrid same, more effective, the geogrid in the same direction as horizontal layer stress. Okay. So this is a summary between mechanically stabilization, or we call it stabilization, versus a mechanism which is tension membrane. So if you do a design, let's say right here, unstabilized layer, you can see that number of passes is about 120,000 equivalent standard axial load. You have got a 10-inch of base course and a 4-inch of asphalt. That is the performance, okay? So the performance over time and the performance of the pavement goes down with time. Now, if you have provide a geogrid layer, you can reduce that thickness and also the asphalt concrete by 1 inch, which is still a lot, about 25%. And you still have 120,000 easel passes, same as the original design, but you save on cost of materials. See that? And the performance will be more or less the same. All right, so save material, but same performance. Now, what happens if I increase this a little bit, but still lower than here? 9 inches of base course and 3.5 inches of asphalt compared to 4 inches, still good saving. I increase the life to 350,000, which is 3 times more than this. So I have savings and I increase the life of the pavement, which is very good. Now, what happens if I keep the same thickness as the original? I increase the life to about 700,000 easels, 6 times the original life. See that? Just by using 1 layer of geogrids. So, and this is where, as a design engineers or as aspiring engineers that's coming out to the society, this is the technology that I can transfer to you and give you some knowledge what is actually happening in the industries. And this is very appropriate that we talk about construction industrial week that have been organized by the university. And I hope that through these particular sharing sessions, you have a glimpse of what is actually happening in the industry and the development in the technology of road pavement. So what have we talked about in our presentations? We have looked at the performance. It's performance, not quality testing. We have to look at performance, putting the geogrid into performance. Even design guidelines are based on performance, nothing based on theory. All right, so everything is empirical. What kind of geosynthetics? What geosynthetics? We have talked about the different kind of geosynthetics already. I've shown you the samples, and then I've identified to you what are the properties, and I also showed you the failure mechanism, which is the tension membrane, or is it by stabilization? Okay, and we have gone through a lot of performance tests in terms of the confinement stabilization. I show you the evidence of how confinement or stabilization geogrids perform much better than high strength geosynthetic materials. And then I also explained to you MSL, how does it work? What are the properties that's required for it to work? And then we look at some of the design issues. Is there a design method existing already for stabilization geogrid? The answer is yes. And we look into what are the documents available now for helping us to specify the properties. You can look at the IOTA document or the Kiwa document certification, which is already available in the market. Right, with that, I finished the presentations. I hope this has been a very interesting session. So I have got about more than 20 minutes available, and I just throw 2 questions for you. Perhaps I will give you some time to think about it. And if you want to shout out the answer to me, by all means, you can shout out the answer to me, and we will see how well you grasp these particular presentations for 1.5 hours. So, okay. So the first question is, what will be the effective, I use the word effective here, function of geosynthetic for road working platform, soft subgrade, and railway ballast track applications. Okay, so I use the word effective here because there are other functions, but I want it to be effective. Okay, that's the first question. So the second question here is define and explain the function you describe in question 1. So they are interrelated. So if you describe the function correctly, then I want you to explain the function to me. Okay. And the third question here is that what kind of geosynthetic will be suitable for the application in question 1? Again, related to question 1. And what are the features of the geosynthetic that can ensure performance? Right. So I hope it's clear to the audience with these 3 questions. So I leave it to the floor. So if the moderator want to take over, you can take over. I will wait for some time for you to grasp what we have discussed. And if you have an answer, just shout out. Unfortunately, we can't be in a classroom where I can see you guys put up your hand. I can't see that. And if you have got the answers, just shout it out and I will try to explain it to you after that. Okay, over to you, the moderator.
Okay, thank you, Dr. Luke, for the informative and interesting sharing. So now I allow to all of the participants to answer the question from Dr. Luke before I open for the others question. Okay. Anyone want to try? What is the answer for exercise 1, 2, and 3?
Anybody who is very daring and bold enough to answer the
Yes.
questions.
Okay.
Or if you are afraid to say anything, type it out. I think Dr. Hassana may be able to write, to read what has been typed out, I think. I don't
Okay,
know.
Dr. Luke, for the
Yeah.
first question, Khairul Izwan answered it. Stabilization, is it?
That's absolutely correct. Yes.
Yes. Mechanical stabilization.
Right. Okay.
Okay,
Congratulations. Thank you.
Okay, anyone from others to answer question 2 and 3 before we open for the question? Or we leave this for your exercise for your class? Is it okay for soil mechanics and foundation class? I think they still search for the answer.
They're still searching for the answer. Okay. Yeah.
Yes. Okay. So now I open the session. I open the floor for the Q&A session. Okay. We welcome any queries you may have, and you can open your mic and answer any question from our speaker. Okay. So I think there are some questions in chat box. So I will read from here.
Okay.
Okay. The first one from Mr. Silva Kumaran. What is the tensile strength for each textile which can be used for root?
What is the tensile strength for each geotextile that can be used for roads?
Yes.
Maybe I should answer your question with another question.
Okay.
All right. So my question to you is when you say that what kind of tensile strength can be used for roads, what do you expect in the performance of the road? Do you expect it to be completely no deformation, or you expect some deformation, or what? If you're saying that I am expecting there's no deformation at all, then I would say that no geosynthetic with high strength can work.
Okay. So actually this is related to CBR value, Dr. Luke?
Well, the CBR value is the strength of the subgrade. Yes, it does relate to the CBR value. But if you are, and I say this throughout the whole presentation, if you are depending on the geosynthetic material strength, it will deform. If you are not depending on interlocking, then it will not work. Okay, so strength is not important here, and this is where the what do you call that, the pitfall in design engineers. A lot of design engineers take a geosynthetic material and they say that, oh, this material has got very good strength, 100 kilonewton, 80 kilonewton. But when you put inside the ground and with a soft soil, it will fail. And you have seen the videos. All right. So to answer Mr. Selvakumar's question, if you are asking what kind of strength of a geosynthetic will be used for the road, I do not recommend any geosynthetic with the strength to be used, but rather I will recommend any geogrid which has got stiffness and stiffness ratio and junction efficiency to be used.
Okay. Okay, thank you, Dr. Luke. I hope they answer the question from Mr. Silva. Okay, the next question is from Noeli Izian. How long is the lifespan of a geogrid in the road use, and it is widely used in Malaysia?
Oh,
the
yes.
lifespan of geogrid.
Yes, the lifespan, okay, all the geogrids or the geogrids that we are talking about is made from polypropylene. You can Google durability of polypropylene, and these are inert material, they are highly durable. The nature of the construction of the geogrid is also very robust in terms of insulation damage, resistance. And so to answer your question, the short answer to that is that in terms of durability, it can be more than 500 years, which is buried inside the ground, not an issue at all. The only concern that you may have is actually installation damage during construction. But the geogrids that we are looking at now here is very robust material that's got no problem with installation of the or installation damage that's going to happen. If you have seen the videos that I show you in the installation, you can see that they unroll the geogrids very easily. And then what happened here is that they actually put the aggregate material, which is sharp, over the geogrids, and you can see that they are very durable and very robust. Okay, so durability point of view, more than 500 years. Installation damage point of view, no issue at all. It is very robust against construction damage.
Thank you, Dr. Luke. And then it is already used in Malaysia?
Oh, yes.
It's been used in Malaysia?
Yes, there's a lot of projects being used in Malaysia. To name a few, Forest City is one of them. WCE, yeah, West Coast Expressway, there are some of them as well. A lot of development projects, we have used that. I think Eco Grandeur, housing development, Sky Sanctuary. So to name a few, yeah, it's been widely used. In fact, we are talking about, if you're talking about worldwide itself, is I can't remember the value, more than 6 million square meters of geogrids has been used in stabilization. So this is a technology which started in the 2007. So is more than 10 years, about 13 years now.
Okay. Okay, Dr. Luke. And we have a question from Refan. Can we use more than one type of geogrid in one road construction? Or can we combine geotextile and geogrid at the same time for the road construction?
Okay, so the first question is, can we combine the different type of geogrids for road construction? My advice to you is not to, because we do not understand the performance of geogrids, other geogrids which does not have the significant radial stiffness ratio and also junction efficiency. All right, so if I look at these geogrids, can you see? Yeah. If you look at this geogrid and this geogrid and combine with this geogrid, we know the junction efficiency of this, but we do not know the junction efficiency of this. What we know is the junction efficiency of this is very poor. Same thing as this. So it's normally not advisable to combine the geogrid's performance. Okay, so that's the first question. Second question is, can we combine geotextiles and also geogrids together? Yes, that is a very good question. The reason being is that the geotextile can act as a separator, and then you have a geogrid which is doing the stabilization work. Okay, so you can combine that. So if you use it on very soft ground, whereby the water content is very high, so I'm just going to show you a piece of examples over here. Just bear with me for a while. Right, if you look at these samples, can you see? Right, you've seen the Geogrid and you can also see the geotextiles. See that? So you can combine them together. Okay, so very good question.
So for the separation and then for the filter, right, Dr.
Yeah, it's basically separation by the geotextile, and the Geogrid will do the stabilization work.
Okay.
So the Geogrid will, so you place your aggregates on top, and the bottom one will face the soft ground.
Okay.
Okay.
Okay, thank you, Dr. Lu. And then for the another question, this is from Silva again. Which geogrid is used for construction and is the best? I think Dr. Lu already explained during the presentation.
Yeah.
So
Well, if I
add,
may, if I may add again, as I said, all geogrids or geosynthetic or geotextile can be used for road construction. Okay. It depends on the performance that you want. If you are okay with a deep rut, then you can use this material, which will give you a deep rut. But if you are saying to me that I don't want to have any rut, or I want to have minimum rut, then I would say that a stabilization geogrid is what you're looking for. All right. So the deep rut by this, it still work. It's just that it deforms so much until your vehicle can pass through. But if you want to top it up at the top, it can still work. You will spend more money, you will spend more material, there are more construction time. So it depends, okay? In some construction, I mean, fill material is very cheap, and the contractor will just say that, okay, I don't need it. I just keep on topping it up. That's fine. All right, so all just synthetic work. So it depends on what kind of performance that you want. All right, so and I mean, if you look from the economic point of view and the construction speed point of view, you would say that, okay, I would prefer this kind of material that I don't have to use a lot of material, a lot of stones, which I don't have, and I speed up my construction. Okay, plus I can also increase my trafficking. All right.
right, Dr. Lu. And then we have question from Aing. I think it is same question as Ili Izian, so I skip this one.
Okay.
So from Tan Xia Ming, Dr. Lu, can we do the curing test on coring? Sorry, can we do the coring test on the road by using Geogrid? And will it affect the function of Geogrid if the Geogrid is damaged during the test?
Good question also. Yes, you can do the coring test. You can do the coring test, but I just want to find out what is the purpose of doing a coring test. Normally, you do a coring test where the Geogrid is used below the asphalt. The reason I'm saying that it's below the asphalt is that this is where the asphalt and the Geogrids and the base course materials stick together. So when you take it out, you can actually look at the samples and you can actually do a compression test. Okay. But if the Geogrid is in the base course material or the sub-base material, they're not going to stick together. So when you do a core, when you take it out, you can see that the whole thing is separated. All right. Maybe that is not what your question is. Okay. Maybe your question is, if you do a coring, will it damage the Geogrids and will it affect the performance of the Geogrid? The answer to that question again is no. I'll give you the reason why. Now, remember when I talk about stabilization geogrid does not depend on strength to perform. Okay? So if you cut the geogrids, you don't have to join it back again. You can place another geogrid at the area where you cut and you will perform because it performs by interlocking. Okay? So if you cut a geogrid, which is a stabilization geogrid like this, it will not affect the performance. It will perform equally well, whatever is still remain on the ground. Okay, so give you an example is that if you have got stabilization geogrid here, and at the servicing area whereby you need to put pipes or you need to put lamp posts, okay, you may core into the geogrids. You make a hole here, and then you put in your lamp post or whatever. that will not affect the performance of the geogrid at all. Okay.
Okay. So we have another question from Harith. I would like to ask, it is suitable to use reinforcement or stabilization for settlement of building? Can you explain briefly based on experience? Thank you.
Very, very good question also. This is an excellent question. Yeah, settlement of building. No geogrids whatsoever can actually assist to reduce settlement. In fact, geosynthetic material accelerates settlement. So that is a very important concept you have to remember. All right. So you cannot put a geogrid and say that, or a geosynthetic material and say that I put it over the soft ground, I'm going to build a house on top. Voila, no problem. It doesn't work. If I know any of the contractors who are doing that, I wouldn't buy the property or I wouldn't buy the house because it's not safe. Okay, so geogrid or geosynthetic materials does not help. Or geotextile does not help to reduce sediment. Okay, and sediment is something that you need to do. And normally, what we do here is that we actually use Plexus or finite element analysis to assess the sediment. But what I can tell you to do by using geosynthetic is that we have another system, what we call is a stratum. Okay, a stratum system is like a cell system. It is 1 meter thick and it consists of cells made up of geogrids. Okay, even that, it does not help to take away sediment at all, but it will reduce differential sediment. Give you an example. If you have got an embankment of maybe, let's say 8 meter high, we used to achieve something about maybe 1 meter, if I'm not mistaken, 1 meter of sediment in terms of calculation. But when you use stratum, which is a design based on BS 8006 for soil reinforcement, when we use stratum, we have got a sediment of less than half a meter. Okay, so which is very good compared to a 1 meter in the calculations without any stratum. So you can use geosynthetic materials or geogrid system to make into cells and to reduce the sediment. And that project, we have used this system for many railway projects. Okay, so we build it over soft ground and then we build railway on top.
Very clear.
So that can be done. Yeah, so that can be done.
Okay, thank you, Dr. Luke. Very clear explanation about this. And then I think we open for the one more question because we have a lot of questions at chat board. Okay.
That's a very good thing. I'm very happy to hear that.
Okay, so the question from Nafratiti, does geotextile perform better in retaining wall compared for the roof application?
Does geotextile perform better? No, geotextile does not perform better in retaining wall. Geogrid should be the one that you use. Okay, so for retaining wall, this is the kind of geogrid that you should use, which I don't have time to talk about. In fact, the topic is so wide, so this is the geogrid that you should use for retaining, which is different from here. You see, this is about interlocking. This is about strength. All right, so this is very strong. So this is the geogrid that you use for retaining wall, not a geotextile. You cannot use a geotextile for retaining wall, the reason being the elongation is way too high. This material has got elongation of the ultimate strength at the ultimate strength of only about 11% or less. If you use a geotextile, which is something like this material, this will have an elongation of more than 50%. So imagine if you've got a geogrid length of 10 meters. It means that your wall is going to move another 5 meters. Okay? So do not design it by geotextile whereby you have a very high elongation. And the other property which is very important is creep. Creep simply means deformation under constant load. It means the load is the same, but the deformation continues over time. So it depends now on the different kind of polymer. So this is made from high density polyethylene. High density polyethylene has got a very good strength and also creep properties. In other words, it doesn't deform as much as a polypropylene.
Dr. Luke, actually there is a special geogrid for retaining wall. That's right?
Well, it's not special. There are many geogrids used for retaining wall, but one of the best one is still this.
Okay, I understand.
Okay, because again, for retaining wall, the design life of retaining wall is 120 years. You must understand and you must know how this material performed for 120 years. And we have got deep knowledge of how this material performed for 120 years. Okay, I can even tell you what the strain will be in 120 years.
Okay.
Okay, because we have good deep knowledge and understanding of the geogrids. If you use material like this, it's not going to perform well because in the retaining wall you got to talk about the facing, so the connection to the facing is going to be a problem with this material. Okay.
Okay, Dr. Luke. So I think I give some time to the participant to answer Dr. Luke's question. So I will give the special gift for anyone to ask the question from Dr. Luke. So please answer the question and leave your name and your address in the chat box.
Well, what I did not say to you is this is not the last slide. I've got 2 more slides after this.
Okay, so
the two slides are the answers.
Okay. So give to the participant maybe in 1 minute.
Yeah, I can wait for 1 minute. Yeah, in 1 minute I will review the answer if you want to.
Okay.
Yeah.
So maybe the participant already searching for the answer. So if you have any idea, any answer, you can answer it. So I will give a special gift to
Very
all
good.
the participants.
Yeah.
Okay,
Yeah,
anyone?
very good.
So the first one is for Cairo, and then there are 2 more questions, 2 and 3.
Yeah, so the first answer is stabilization, which is correct. So now the second question is explain stabilization function. Okay.
Zata, you want to try for second answer, a second question? Zato? Najib, where is Najib?
The answer for
Okay, Harith.
The answer for question number 2 is on the chat.
What, Harith? Can you repeat?
It's on the chat. It's on the chat.
Okay. Right, Dr. Lu?
I didn't see the chat. Yeah. Why don't you read it?
Oh, in the chat. Okay, sorry.
Yeah.
Wait. Answer from Harith. Okay. The answer for third question. For the second question, the stabilization have more radial stiffness, which will overcome the deformation of the root after 1000 pass. Is right?
No, not accurate answer. Somewhere there, but it's not accurate.
Okay.
Yeah.
But good try.
Good try. Yeah, very good try.
So, Cairo and Harith, please leave your name and address. So I will contact you later. So I think Dr. Luke can proceed with another slide. You can
Okay.
continue.
All right. So let me just give you the answer. So the first one is mechanical stabilization or confinement or interlocking. So somebody got it right. The second answer is found in slide number 34. Which give you the definitions or the description of stabilization. So it's improved the mechanical behavior of unbound granular material by including one or more just synthetic layers. So the key words I want to see here is, if you tell me it's reduce deformation and reduce minimizing movements of aggregate, then you got it perfect. Okay, that's what stabilization means. Stabilization means to reduce deformation or minimizing movements of the aggregates. Okay, by what? By interlocking, by confinement, due to the geogrids. All right, I hope this is very clear now because I keep repeating this over and over again. All right, that's a function of stabilization. So if I go back to all the way back again, let me just see whether I can get this. Remember the 2 definition I gave it to you in terms of reinforcement. Yeah, right here. Yep, right here. Remember this slide? Okay, so I give you the definition for reinforcement and also the definition for stabilization. So it's very important to remember stabilization is to reduce deformation, to minimize movements of the aggregate, which is the aggregate of the base material. Okay, the base cost or the sub-base cost. Right, and the third question is what will be the property? And I think, oops, sorry, yeah. So the third question will be, what will be the property? So what kind of geosynthetic are suitable for the application in question 1, and what are the features of the geosynthetic that ensure performance? So somebody gave an answer earlier, and that answer is actually for third question. All right, so is rigid multi-axial geogrids, for example, the hexagonal geogrid or triax geogrids, with high junction efficiency and high radial stiffness at 0.5% and radial stiffness ratio more than 0.75%. So if your answer is high efficiency, junction efficiency, radial stiffness and radial stiffness ratio, then you got it correct.
Yes.
Okay?
Okay.
So that will be a good exercise, and that will be officially end my talk. So again, thank you so much for all the participation and the number of questions that comes in. I think this has been what do you call that, exciting. I hope you learned from here, and need any help whatsoever, I mean, please go to your respective lecturers, Dr. Hassana, or you can contact me directly, and I'll be glad to help and also to share with you what the industries have been doing in terms of evolving technology. And we at the forefront of the application will know best what will be the best for industries, and that's what we are trying to do. And being an innovative organization, that's what we are evolving in terms of having more innovation in our product development. Okay, all right. Thank you again to all for attending this session.
Okay, thank you, Dr. Lu. So, well, I think that's all for Q&A session and presentation from Dr. Lu. Once again, thank you very much to Dr. Lu due to the very great presentation, and I think there are a lot of information that we can use for me and for students for their future and for their career. So for soil mechanics student, maybe it will be used for your test or final. Okay, so and then I will pass the session to our MC, Miss Zato. Okay, Miss Zato, are you here? Okay. Miss Sato still with us? Okay, it's okay.
Miss Yusrina, you forgot to turn on your mic.
Oh, sorry.
Okay.
Okay, now I need everyone cooperation to switch on the camera for photography session.
Can we ask Dr. Luke to stop the sharing first?
Right, so what I do is stop share.
Okay, thank you.
How do you do a photography session?
Just screenshot it.
Okay.
Okay, I will be in charge for photo session. So smile everyone, turn on your video, give me your bestest smile. Okay, I have 132, so it's going to take a while. Taking the first picture, 1, 2,